Hello, folks. Welcome to Rational Science, the only site on the internet that does physics. Everybody else does mathematics. What is mathematics? The movement of concepts. They move concepts around. They think they're doing physics. That's the problem. They move the mass, they transfer energy or information, they vibrate the field, and others shake the plasma or what is it, the ether? No, none of that is physics. You cannot use concepts as physical objects. That's the main point. Okay, and that's primarily what we argue here in this channel. Okay, so when you're using mathematical concepts as physical objects, you are not doing physics, you're doing irrationality. Okay, that's the argument. Anyways, we're going to start with our extinction segment today. And we have a couple things to say, especially about what we said last time about the dinosaurs, whether birds are dinosaurs. Some people think they are, so we're going to answer that question today. But let's begin here with something else first, and this is the state of the union. We'll call it the state of the world. Okay, it's the state of the world, right? And here it is, just a sample. Battle lines: Israel rejects ceasefire. How Iranian drones changed warfare, and what's going wrong for China's economy. And this is out of the Telegraph in Great Britain. What is it, England, right? Across the world, from Europe to Asia, from the Americas to the Middle East, tensions are rising between nation states as the traditional alliances and alignments evolve in the 21st century. 2024 sees war in Europe and Israel and elections in major economies from the US and the UK to Taiwan. Insurgencies flare in Yemen and Burma, tensions that escalate in East Africa, and all around the world, the international security architecture buckles under increasing pressure. Wars and tensions, fault lines grind and slip in an increasingly dangerous and confusing multipolar world. I think that's a pretty good summary, okay, of the state of the world. And it's a little disheartening, but I think it was predictable that that we would end up like this. We're getting to the point where there's only three empires on planet Earth, or three real powers out there: Russia, China, and the United States, together with its allies, right? And those three groups, actually, it's two groups. You could say the U.S. and its allies against Russia, China together, and maybe tomorrow with the Arabs all against the U.S. and its allies. So it's a maybe bipolar world, and I think that was inevitable to some degree because, again, I don't think any empire is going to conquer the whole planet. At some point, there either is going to be war, or I think there is going to be war. I don't think you're going to avoid it because the interests of one mafia encroach on the interests of another mafia. And I don't think that's avoidable. Again, that's my take on that. I think that was predictable, and that's why I think we're getting we're living in a dangerous world, but we're getting to the point where, extinction is around the corner. We're on the last stretch. How long it's going to last, I don't know. Will I see it? I don't know. I'm in my 70s. Maybe I won't see it. I don't know. Maybe I will. Maybe I won't. We'll find out, right? But I think it's very close. That's the way I look at it. Okay? Just an opinion. Okay. What's the mechanism for the extinction of man? The collapse of the global economy. Does that include wars? Of course it does. It has to include wars because there's a fight for resources or for expanding the interests of one mafia at the expense of another. That's what it's all about. And at some point, the economy, the global economy collapses. We cannot grow economically, right? Humans cannot grow economically. Their economy cannot grow forever. At some point it stops. And there was a book saying, grow or die. And I think that's more or less summarizes it. Yeah, we either grow or we die. And if the global economy cannot grow, it will die. What is the death? Extinction. Okay, okay, and here's another take on that. Similar, right? Powell, who's Federal Reserve chief there, says the U.S. federal government is on an unsustainable path, and that just means that the debt is growing faster than the economy. So it is unsustainable. I don't think that's at all controversial, Powell said when asked if the national debt is a danger to the economy. Yeah, it is a danger to the economy, and the danger to the economy is the danger to humans because once the economy is gone, we're all dead. Okay, and the important thing here is that the United States is too big to fail. The United States. I mean, if you get little countries out there, maybe Argentina, with Milei, Uganda, or who knows, I don't know, Romania. It doesn't matter. Someone will bail them out. No one bails the United States out except the Klingons, maybe, coming down here and giving us a hand. The United States is where the buck stops. The United States too big to fail. It says here the U.S. national debt topped 34 trillion for the first time ever in early January, just over 3 months after surpassing the 33 trillion mark. Okay, according to data released, right? And so what's happening? We're growing a trillion per month. So yeah, that's no laughing matter. It really ain't. But the debt is growing by the trillions, and I don't think we're producing by the trillions. So all we're doing is producing money to cover the debt, and that's exceeding the production. And I don't think that's sustainable. So I agree with Powell. It's unsustainable. But I'm not sure how they can reverse course. I really don't. No magic trick in economics as far as that's concerned. Congress has punted on spending deadlines 3 times since the end of September. Okay, and under the latest stopgap measure passed in January, funding for 4 federal agencies will expire on March 1st. Funding for the rest of the government is set to run out on March 8th. Yeah, and these are constant deadlines. Every month it looks like they have to reevaluate, and Congress has to decide whether they're going to print more money to cover the debt hole. And all that does is weaken the real value of worker salaries. They always lag behind. So little by little, the worker, the proletarian, the person who depends on a salary, that person falls behind and behind and behind. And, today, even 2 salaries, wife and husband, I don't think even they can make it to the end of the month or barely make it. So I don't know where that's going to end. At some point, that's going to have an effect, especially when all these countries are depending on the United States. They're clinging on to the United States, and they're doing a lot worse. In other countries, like, for example, Argentina is a good example. The workers can barely make it to the end of the month. And so there's going to be riots over there before they reach the United States. But the only way they're going to get out of the mess is if the United States, the World Bank, International Monetary Fund, one of those organizations, helps them out. Meaning they have to produce more money, meaning they devalue the coin even further. And so I think it's an unsustainable process. Okay, and so at some point the global economy will crash, and it will not be a depression. It will be extinction. Okay, last week I talked about this issue, which is of interest to me, and it's a fellow says dinosaurs didn't go extinct. Why? Because he says the birds are dinosaurs and they're still around. Okay, so that's his take on that. What do I have to say about that? Well, here it is. This is more or less what I have to say. I said that if you look up the word bird, right, it says that they were archosaurs. It says, archosaurs is a clade of diapsid tetrapods, with birds and crocodiles being the only living representatives. So the fact that, we have birds and also crocodiles for that matter means that the archosaurs never disappeared. And that's kind of strange because the Triassic is known as the age of archosaurs, and they went extinct. And this all wants you to believe that birds and crocodiles are still alive, meaning the archosaurs are still alive. They never became extinct. And it turns out that the birds were also dinosaurs, apparently, or part of the dinosaur clade or order or whatever. And it turns out that that means that the dinosaurs didn't go extinct. So let's see, we don't have archosaurs; they never went extinct. The dinosaurs never went extinct, and he's going to make a case that even the synapsids never went extinct. So I guess no animal ever went extinct. No, we can't talk about extinction now because no animal, no big grouping of animals ever went extinct. There have been no mass extinctions. Okay, so that's the issue here. Okay, let's see what he's got to say. Okay, he says, Wikipedia entries, you are wrong about birds. That's what he's saying to me. About this entry, you say, here it says that they, the birds, right, were not dinosaurs. They were archosaurs, right? That's what I just showed. The fact that you look up the word birds and it says they were archosaurs. You look at the word archosaur and it includes the birds. And the archosaurs died at the end of the Triassic. I mean, that's what we all thought, right? Now this fellow says, no, they didn't die. The archosaurs are still around and so are the dinos, right? And so it says, but the entry does not say the birds are not dinosaurs. Okay, it says that the birds are archosaurs. And I guess it's terrible when you have to explain a joke to someone. Yes, I did say that on purpose because it's irrational to say that the dinosaurs are still around. So I said, well, so I was really playing with it and saying, look, it says here, just acting dumb here, right? That the birds are archosaurs. And you say they're dinosaurs, but here it says that they're archosaurs. What are they? Are they archosaurs or dinosaurs? He says, well, they're kind of both. That's his answer. And so this is what I say here. I say, in fact, he repeats what I say, and it says, you continue. They're not saying that they were not dinosaurs, but that they're archosaurs. Right, so I did clarify that, and I don't know why he had to raise the fact that I said that they were not dinosaurs. I said first, they're not dinosaurs, then I corrected on purpose always, saying, well, they're both, but what's the point? The point here is that we're not talking about clades, we're not talking about scientific, precise scientific definitions of these animals. What we're talking about is extinction. And this doesn't go through his mind. He doesn't understand that this has to do with extinction and not with the names of animals, the clades and the nomenclature for all these different kinds of groupings, right? That's the issue. And I said it last time, but he didn't understand it. So here we have to rehash what happened, okay? And so he says, archosaurs includes birds. Yeah. Birds are dinosaurs. Yeah. They're both. So are birds dinosaurs or are they archosaurs, I ask, right? And he says the answer to this question is that birds are archosaurs and that they are dinosaurs. There is no contradiction here. And again, he missed the point completely. He missed the joke. He still doesn't understand the joke, I guess. It's terrible when you have to explain a joke. It's not as funny, So what does he say? His conclusion is, yes, some dinosaurs are extinct. But the fact that many species of dinosaurs are extinct does not obviously imply that all dinosaurs are extinct. Okay? Yes, some synapsids are extinct, but this fact is perfectly consistent with the fact that there are synapsids that are not extinct. Synapsids like Homo sapiens. Okay? So he continues here one more. Let me show this before I answer. And he says, now look at their entry for, meaning the Wikipedia entry for synapsids. It says, the synapsids were the dominant land animals in the late Paleozoic. The only group that survived into the Cenozoic are mammals. Mammals are a group of synapsids. Okay, yeah, okay. And since humans are mammals, humans are synapsids. Since my mother is human, she is a synapsid. Okay, so his mother is a synapsid. I was not aware of that synapsids were still around today. So what are we talking about? You can see because of his way of confronting this problem, he's going to run into trouble no matter what he says. Okay, and that's why we have to keep the specific categories. The clades, what they study in biology and what they study in paleontology has nothing to do, in detail, has nothing to do with the question. Are humans synapsids? Irrelevant question. Are birds dinosaurs? Irrelevant question. Okay? None of those questions have anything to do with the issue that we have before us. Okay? What we have before us is we have an extinction 65 million years ago, and at the end of the Cretaceous, and we say that the dinosaurs became extinct. That's what we say. And you cannot say, well, the birds survived. Well, yeah, other animals survived as well. Mammals survived, for example. The issue is we call that extinction a dinosaur extinction because we need to talk about extinction, not about the dinos. Okay? And the same for the Triassic archosaurs. What died at the end of the Triassic were the archosaurs. We killed them all, 150% of them, all of them. And you can't say, well, some survived because they're over here today. Yeah, we called it Triassic extinction. In order to refer to the extinction, we say it's an archosaur extinction. The other one is a dinosaur extinction. Okay? And you have the Jurassic dinosaurs and you have the Cretaceous dinosaurs. But we do not include birds in that grouping because, the birds do not fit in the category of the land dinosaurs that we're talking about when we talk about extinction. That's the issue. Otherwise, this fellow is coming up with different categories. He invented essentially two extra categories. Those are the other dinosaurs, and the birds are these dinosaurs. So we have the those and the these. Okay, and so we cannot talk in that way about extinction. We cannot say, oh, those dinosaurs became extinct, but not these dinosaurs, right? I can't imagine this guy calling the cops one day and saying, calling them to the house. Cops come in there and say, what happened, sir? Well, what happened is, the dinosaurs are not extinct. Oh, the dinosaurs are not, you see, okay, and says, yeah, a couple of dinosaurs were flying around my house last night. I see. And one of them shot through my chimney and messed up my fireplace here. I see, okay, well, sir, don't worry, we just called some men. They're going to come here in white jackets and they're going to take you to a nice place that has flowers and padded walls and, you'll be okay over there. Yeah, you cannot talk in the context of the Cretaceous extinction about birds, okay? We use the word bird to refer to the birds that survived and went into the quaternary. And those that died, we call them dinosaurs, okay? And so we're referring to that context. That's the context. Dinosaurs died at the 65 million years ago at the end of the Cretaceous. And so all these little categories, whether they belong to synapsids or to Triassic archosaurs or to dinosaurs, whether the birds are here and the crocodiles are over there, it's irrelevant. Irrelevant to the question we're dealing with here. We're dealing with extinction, not with animals. Okay? That's the best way I can put it. So that you focus on extinction, on the word extinction, not the word bird and dinosaurs and archosaurs. And I don't know how else to put that. If you don't understand it, well, sorry. It's irrational to say that the dinosaurs did not become extinct 65 million years ago because the birds are still around flying around your chimney. Okay, so this is what he's got. He says those theropods became extinct, and theropods were the T-Rexes. Those are known as theropods, right? And he's talking about those theropods and these theropods. The birds are theropods, but it turns out that the Triceratopses, they don't fit under theropods. They were, as you see, ornithischia. Let's see if I can pronounce that. Ornithischia. Okay, ornithischia. And that means that they have a bird hip. So even though the Triceratops had features of birds, they're not considered theropods, but the birds are considered theropods and not the other grouping. And so, again, all these details have nothing to do with the question that we have before us, which is the extinction of the dinosaurs at the end of the Cretaceous. Okay, so T-Rex is a theropod, but Triceratops is not. Okay, and that's the context. It's the context that we're talking about, and I don't know if it's sunk in this individual's mind. Okay, here I showed you this the other day again. The Permian, the first half was the age of pelycosaurs. They were all synapses, all these animals. And at the end of the Permian, which is at the end of the age of therapsids, what died were all the synapses. We say that what died were all the synapses, 150, 175% of them, all of them. Okay. Now, are mammals descended from the synapses? Yeah. We're also descended from some amphibian that was in the Carboniferous, and we're likely, and we can probably trace our lineage all the way to the Cambrian. Okay, so does that mean that the fish of the Devonian did not die because the placoderms they didn't die because we're still around and we descend from them? So there was never an extinction in the Devonian. We descend from the synapsids of the Permian, and so the synapsids in the Permian didn't die because we're still around. So how are you going to talk about it if you're going to be so specific with the language? Obviously, the language, the precise language that they use in paleontology has no bearing on the question when we're talking about extinction. That's the issue. And I don't know how else to reinforce that. Okay, and here's another one that I showed the other day. You have the Jurassic dinosaurs. They were a little different than the ones that came out in the Cretaceous. There were more long necks in the Jurassic, even though there were a couple long necks also in the Cretaceous. But they were primarily, you can see that just morphologically they were different. Okay, so there was an extinction at the end of the Jurassic, and there was another one at the end of the Cretaceous of different kinds of dinosaurs. Okay, but we put all these in the same bag and call them dinosaurs. Okay. Do you see any birds in there? No, you won't see any birds in there because we don't consider birds dinosaurs for the purposes of extinction. Okay, we say that the land dinosaurs, the terrestrial dinosaurs, were the ones who went extinct. There were no aquatic dinosaurs. All those aquatic that many people confuse with dinosaurs, they were reptiles, and there were also flying reptiles. All those died as well, 100% of them. There are no more flying reptiles, no more aquatic reptiles today. Okay, those died at the end of the Cretaceous. And so we have the flying and swimming reptiles, and we have the terrestrial dinosaurs. Those went extinct. That's the only way we can talk about it. And if we put the word bird in there, we just mess things up. We can't use the word bird together with the word extinction of the dinosaurs. It's just a different context. Okay, and how did they die at the end of the Cretaceous? Well, here you have a note that I found in Britannica. The evolution of cycadioids seemed to have paralleled the rise and fall of the dinosaurs. Exactly. It was food that killed all the dinosaurs. It was the last bit that killed them. There was already a decline in species diversity, but primarily there you have the answer to the question of extinction. Okay, when the cycadioids disappeared, the dinosaurs disappeared. Okay, and the problem here is that paleontologists, many of them believe that it's a food-related issue, but the question is, why did the food disappear? And so they come up with all these catastrophes. Many of them come up with catastrophes to explain the sudden disappearance of food when we don't need any catastrophe. All food will eventually disappear for every type of animal that's ever lived. Food, the plants don't last forever. They're replaced by other plants, and the animals that have become used to those plants, that develop some kind of a symbiotic relationship with them, eat and then poop and then eat and poop and they pollinate and so on. Well, when that process comes to an end, the plants disappeared, so do the animals that depended on that food. They cannot switch overnight and say, look, I'm a rabbit, I eat lettuce, but there's no lettuce, I'll eat just pine trees. No, pine leaves or whatever. No, you can't. Rabbits don't eat pine leaves. They cannot switch overnight from lettuce to pine leaves. Okay? And so this is where people make the mistake. They think animals, including us, right, that we could switch food anytime we want. Oh, we can't eat. There's no more lettuce, no more tomatoes, no more peaches. No problem. I'll just eat pine leaves. No, it doesn't work that way. Okay? And you can't eat, ferns, for example. They're poisonous. So we cannot switch overnight. And that's what happened to all these animals. When the food started to disappear, when their islands began to shrink over the millions of years, the last few million years, their jungles, their forests shrunk, partly pushed inwards by the growing vegetation that was to feed the next generation of animals. Okay, so I call it the shrinking island because here you find. Let's talk about the dinosaurs. Dinosaurs they're in heaven. They're in this Eden, and they have all the food they want, and so they're eating cycadioids every day. They just eat, munch, no problem. They reproduce, but it turns out that the angiosperms, they're growing all around and squatting the land and taking over land that was previously occupied by conifers such as cycads and cycadioids, ginkgos, and so on. And so what's the problem? The problem is that now those animals that depended on that source of food find less and less food, even though they have multiplied in numbers. And whereas you got all these tiny little animals called mammals, and they're growing with a new vegetation. And so what happens is the island is shrinking on the dinos. At some point, there's a critical point where that system collapses, the dinosaurs die, and now the little animals, can expand together with the angiosperms first, and second, they can radiate, they can multiply and become bigger and become the animals that we have today. That's the process that I'm saying for extinction. That's why the only thing you have to explain in the world of extinction is selectivity. How does Mother Nature ensure that these groups of animals, the old ones especially, chronologically older, animals disappeared, and the new generation continues as if nothing happened? Well, they belong to two different food chains. That's the issue. And so one food chain goes away and the other one continues. That's why a mass extinction is the disappearance of a food chain. It's a food issue. And why does the food disappear? It disappears because food, plants don't last forever. They have their cycles too. And when the plant has to go because it's been around for too long, they lost their genetic diversity, they're squashed by more vibrant, more modern plants that are, grow faster and squat the land. And so they're choked. Their populations are choked. And any animal that depended on that source of food goes with it. That's the mechanism we're proposing. Okay, here's a graph that I like to show all the time. It's an important one because it synthesizes why the dinosaurs disappeared. And here you have it. No asteroid, no volcanoes, no climate change, no diseases, no egg predation, none of that nonsense. There's what is it? The supernovas. No, here you see it. Here you see what happened to these animals. Okay, and it is that the blue there that you see, the angiosperms, over the last 3/4 of the Cretaceous, they took over the land. Number of species multiplied, and I'm sure the number of plants as well multiplied for angiosperms, and they squatted the land and they squashed out. They squashed out the cycads, ferns, and other conifers, and so on. So this is what happened. There you see it. Who grew with the blue ones? The mammals. We are angiosperm eaters. We do not eat cycads. We do not eat ferns or conifers of any kind, ginkgos or cycadioids or any of those. So that's what happened. And this graph was made after 4-year study by a group, okay, that looked at all the data from different papers. And so after 4-year study, they were able to concoct this graph. So this graph is not mine. I just borrowed it so that I can make my point. And the point is that angiosperms pushed the conifers out. What died at the end of the Cretaceous were the conifers. And again, this person might say, "Oh, but the conifers are still around." Yeah, but they're not dominant anymore. What's dominant on the planet today are angiosperms. So we just say the conifers died, or if you prefer, the cycadioids or the cycads or the ginkgo bilobas, and any of those died. Okay, something died, some plant died at the end of the Cretaceous, and we call them cycads, cycadioids. You can refer to them as conifers. Does that mean all conifers disappeared? No, it means that they no longer reigned. They were taken over. A new plant became the ruler of the planet, and those were the angiosperms. And the dinosaurs did not eat angiosperms. There's a couple paper out there that argue that they did. There could have been an exception. I'm not going to dispute that, but 99% of the dinosaurs ate conifers, specifically cycads and cycadioids. And what happened is those forests, those jungles disappeared towards the end of the Cretaceous. And that's when all the herbivores that depended on that source of food disappeared with it. And right after, all the theropods, the big guys, the T-Rexes and so on, the big dinosaurs, the carnivores, they disappeared with them. So it's a food issue. And that's why in order to talk intelligently, we cannot confuse birds with dinosaurs when we're talking about extinction, especially 65 million years ago. The word bird should not be included in there at all. Okay? But if people want to say, hey, the birds are still flying around, the dinosaurs are still flying around my house, well, yeah, go ahead. I mean, I hope they treat you nice at the funny farm. Okay, here you see again, just another graph here. Shows you what happened in each era, and they're all related to food. You got the non-vasculars and early vasculars in the Devonian and Carboniferous. Then you go into the seed fern region where you have the first half. In the Permian, there you see what disappeared were the glossopterids, and at the end of the Triassic, what disappeared were the dicroidiums. Glossopterids and dicroidiums are both seed ferns. We have no seed ferns today. They all died at the end of the Triassic. And again, the synapsids depended on glossopterids, and the archosaurs depended on dicroidiums. When if you look at the age of the Triassic, that whole period, dicroidiums you can call it the age of dicroidiums. They started with the Triassic, they ended with the Triassic. Guess what? The archosaurs ate? Well, they ate dicroidiums. And I'm sure birds don't eat dicroidiums. Okay? And likewise, humans don't eat glossopterids. Okay? If they were still around, they would not be able to eat those seed ferns. So yeah, you can divide the cake any way you want. In the case of when you go into the details of how you're going to classify animals and plants, you can go into a lot of detail, and it depends on how you cut the cake. Are you going to decide to name animals according to what they eat? Are you going to decide according to their morphology, their bones? Or are you going to decide it on the basis of, clades, cladistic analysis, who was my father, who was my grandfather? There's many ways of classifying families of animals. And that's why you have all these fights in paleontology, because that guy sees some features that this guy doesn't care about, and vice versa. And so each one has this classification system that they're developing still, even to this day, as more samples come out of the ground. And so, we don't worry about that when we talk about extinction. When we talk about extinction, it's very clear. Synapsids died at the end of the Permian, archosaurs at the end of the Triassic, and dinosaurs. There were two extinctions. One, which was, we can say that also about the Permian for that matter, You can see the pelycosaurs died at the end of the Olsen extinction, which is midway into the Permian, and then what continued were another type of synapsids. They were known as therapsids in the case of the carnivores, and maybe pariasaurs is an example of the herbivores. Okay, so there were two types of synapsids during the whole Permian period. Triassic, archosaurs. Dinosaurs, two extinctions, one Jurassic, one Cretaceous. We call those terrestrial animals, big animals that ruled the planet. We call those dinosaurs. We don't call birds dinosaurs in that context. Okay? Irrelevant if birds descended or a parallel line of dinosaurs. Again, birds don't eat, they neither eat ferns, nor do they eat conifers of any kind. And so even if, I'm sure if we bring the cycadioids back to life, I think the birds would not eat them. And so if we classify animals by what they ate, we're going to eliminate completely birds from the dinosaur lineage. So again, it depends on how you want to cut the cake, where, vertically or horizontally. Okay, let's move on to some of the questions people asked since last time. Okay, let's find out what people are interested in asking, and there were quite a few questions and comments, so it's going to take a little while to go through all this. Bear with me. Let's see if you see your own comment there, and then you can criticize me and throw rotten tomatoes at me. In fact, that's how we start this. Fellow says the following. He says, I have never seen a channel with a more polar opposite name. Rational science. You are a glue eater with no idea what you are talking about, or in an insult to all of science. I highly recommend deleting your content and or apologizing for disseminating false information. Loved it. Absolutely loved it. Okay, thank you. Thank you for your comment. We will be taken into consideration. I guess he was upset about something I said. I guess, I don't know. And another fellow along the same lines, more or less, right? He says, you are absolutely correct with respect to black holes, right? That is why we have no electricity, lasers, nuclear power plants, nuclear bombs, computers, or molecules. Pure genius. Yeah, these people believe that science is about technology and technology is about science. They mix the two words. They think that science and technology are synonyms or one is related to the other. They're not. Okay, they're not. Mathematics, the religion of mathematical physics, is something else. They work together with technology, and when they invent something in technology, they get a Nobel Prize in so-called physics. Okay, and it's technology, and they call it, physics. No, technology has nothing to do with physics, the science known as physics. Okay, so that's why we have to define these terms. We have to find out what science is about. First, we got to define science, then we have to define physics. Okay, and neither of those two include technology. Okay, science has to do with rational explanations. You need to have a mechanism, or in the case of philosophy, you have to explain purposes and reasons for someone. When you get to physics, you have to explain mechanisms. Causes and mechanisms. That's what physics is. And to explain causes and mechanisms, we cannot say that, technology. No, technology has nothing to do at all with physics. Are we supposed to say that quantum mechanics is proven because computers are around? Does the fact that we have computers, does that prove quantum mechanics? Well, the fact that we have computers, does that prove that a particle can be at two places at once, which is the explanation that the mathematical physicists, so-called mathematical physicists, mathematicians, that's the explanation they give you. They say that a particle can be at two places at once. So does a computer prove the fact that we developed, that we have this technology known as computer, does that prove that a particle can be at two places at once? How about GPS? Does that prove that that time is a physical object that can be bent? Is that what GPS proves? So again, this person obviously went to some kind of monastery. That's where they taught him. And this is what he parrots. He just repeats it without knowing what he's saying. No, technology does not prove theories. Okay? Theories have nothing at all to do with technology. Theory, you have to explain the mechanism objectively so that we understand it. You want to tell me how a car works? You say, well, the gas comes over here, goes through the pipe, goes to the carburetor and the pistons and so on. Then you explain the mechanism. Do I believe that's the way it works? Well, someone else might have a different theory. He might say, well, no, it's angels, it's spirits that go from the tank through the pipe all the way to the motor. And that's his theory. He believes in that angels do it or spirits do it. And this guy says, no, it's not. It's the gas and, okay. Different theories. You can believe whichever one you want. We just want to understand what each one has in his mind. This guy explains it with angels. The other guy explains it with gasoline. Others say energy. We don't know what that is, so I don't know which is better, the spirit or the energy. Which one is a better explanation? But that's where we're at today. So explanations of mechanisms have nothing at all to do with technology, with developing a gadget. Okay? The fact that you can pick up pins with a magnet, that's useful for technology. You can do a lot of stuff with that once you discover that event, that phenomenon. But that doesn't mean you know how to explain how the magnet actually did, how it pulled up every pin. So-called field, right? You cannot explain what a field is or what's inside the field in that region of numbers. Okay, so someone says, I thought the ether was the black stuff. Yeah, a lot of people confuse, or they have different opinions, you can say, or you can say assumptions. Some people assume that the white dots are the ether. Other people assume that the black stuff, space and ether are synonyms. So they have these both versions, and so you have to be careful about, first you got to get from the ether is which one he favors so that you can follow his presentation. Some etherists believe or propose or make an assumption, a supposition that space and ether are the same thing. Others think that it's just a bunch of particles within space. And if they're particles, then something has to give shape or backdrop, provide a backdrop, provide some background to each particle, contour it, and so on. And we need to identify what that black stuff is. And so in that case, we call that space, and the ether are just the particles. So we have this problem out there, and every etherist has to tell the crowd. It's up to them to tell the crowd, right? They can't say, well, I don't know because I've never seen the ether, but let me tell you my theory. No, you can stick your theory up your nose hole, okay? We don't care about your theory. We need to know what you mean by ether. And if it's a physical object, draw it. Make an illustration. Make a mock-up. Make a statue. Whatever. But bring something that has shape. Put it in front of our eyes. And if it's a concept, define it. Very simple. So you have to tell us if ether is a concept or an object. And if it's an object, illustrate it. If it's a concept, define it. Very simple. And if you're going to put it as an object and there's a background, something giving it shape, you got to tell us what that background is as well. Okay, last week, this fellow said ether must be composed of some form of object. Okay, fine. We call it particles, right? I'll simply refer to them as bits. Okay, bits, particles, same difference. They're all tiny bits of a larger ether medium. These bits are the smallest scales object. We don't care. You already said bits are particles. That's all you said. They are not made of smaller objects. Okay, so we don't care what the bits are made out of, but a bit is a particle. And there you have it. All you said is what we've always understood for what the ether is. You haven't come up with anything new. So he went on ranting for quite a while. They were writing a long message. And all he said is the ether, what you've always said it is, Bill, bunch of particles. See how easy it was? You didn't have to say all that stuff and that they move and that there's a distance between the particles and so on. We just need to know what the ether is. And ether is a concept. It's not a physical object. As you can see, It doesn't stand still because those particles are always vibrating, changing their distance with respect to each other constantly. That's the supposition, that's the assumption, okay? That ether is just a bunch of particles, and when they vibrate, those are the waves that we call light. Okay, that's what it's always been like that since the day that they invented the word ether, which just means, the air of the gods. It's what the gods breathe. And ether is not an object because an object has to have shape. The ether is infinite, just like space is infinite according to all these people, and there is no such thing as an infinite object. So you have to tell us what the ether is. Okay, and the guy didn't like my answer, so he said, so all I need is to define my terms and you would consider it to be rational. Well, yeah, you have to define, or if it's a concept, you have to define it. If it's an object, you have to draw it. You have to illustrate it. So it's one or the other. How are you going to treat the ether? Are you going to say it's a physical object like a table? A table we don't define. We point to it so that the person understands the word table. We say that's a table. We point to it. And so that's what you got to do with the ether if the ether is an object. We don't care what it's made out of. We don't care about the bits and particles and molecules and atoms it's made out of. None of that matters. You point to the whole shebang. We don't say an elephant is 1 trillion atoms because a table is also 1 trillion atoms, and so is a rock and a tree. So we don't define these words, or we don't use these words to refer to what it's made out of. Okay, we point and say tree, and we refer to the whole thing. And when we point to a tree in physics, right? In physics, when you point to an object, that object is made of a single piece. There's no mereology, no little parts time pieces, moving. There's none of that. It's made out of a single piece that's standing still. You point to a tree and say tree. That tree is made out of a single piece. For the purposes of presenting the object. Okay, the table is made out of a single piece. The house is made out of a single piece. You are made of a single piece. You're not made of atoms. You're not made of molecules. You're not made of cells. You're made of a single piece when I say man or whatever I want to call you. I can call you X. X is made out of a single piece in physics for the purposes of presenting an object. You don't say, well, it's 1 trillion atoms. Let me tell you what it's made out of and how it moves. No. All objects are static objects. You point and name. That's it, period. Okay? So if someone defines an ether as a medium meaning thing, object. Okay? Medium is object. It's a synonym of object in physics. Suddenly you consider ethers as rational. But no, you can't define the ether as a medium because medium you point to. You define concepts. Okay, so you got to decide again whether ether is an object or a concept. There's only 2 types of words in the entire dictionary. All words fit under concept or they fit under object. They can't fit in both ways. Either they have shape or they don't. That's how simple it is. So concepts we define, object we point to. So you need to go to kindergarten physics to understand that. Okay, you skipped kindergarten. Okay, and so we define concepts. Okay, so you have to tell us what your ether is. Is it concept or object? We don't care what it's made out of. Okay, you keep changing the rules. I do. Well, I thought I'm very consistent with my rules. I thought that I guess he's referring to mechanism when he says it needed to be object-based to be rational. Yeah, mechanism has to be object-based. If you're going to talk about a car, hopefully you have objects in front of you. You know how a car works or how it moves, etc. Then you have to have, you're talking about a mechanism, right? And in that case, yeah, you need to point to some kind of object. I'm not sure if you remove all objects in the universe, what's happening? What are you pointing to? What's happening? What's there? What experiment you're going to run? What are you going to measure? Etc. 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 There's nothing there. So yeah, when you explain a mechanism, you had better have objects and not concepts. You cannot say that. Let me explain energy. There's nothing to explain in energy because energy is not an object. You cannot explain the mechanism of energy. Yeah. Okay, let me guess. Only acceptance of your electromagnetic rope hypothesis without question is rational. No. In science, we do not accept. Accept means believe. means that you have knowledge, which is another word for belief, and we do not use belief in science. In science, we only explain as it relates to physics, we only explain mechanisms and causes. That's physics, okay? And so we don't accept, you don't have to believe the theory. When you talk about belief, you go to church, you go to a religion, okay? You step the line outside of physics, and now you're in religion. So we don't care what you believe in, or whether you accept it or not, whether they convinced you, whether you call it proof or knowledge. None of that has anything to do with physics. In physics, objective explanation of a mechanism. Period. We're not, or causes. We're done. That's where it ends. Okay. A couple more issues here. One fellow says, let's see if we can get this up here. Says concept, an abstract idea. Well, that's a bad definition. You got to work on it a little more, because abstract is, you look it up, it's an adjective, it means conceptual. And idea, any conception. So all he said is concept is a conceptual conception. So yeah, that's what happens when people just pull out a definition out of the dictionary and just place it up there. All they can do is copy and paste. And they never realized that the people who wrote those definitions to begin with did the same thing. They just said, well, what does it mean out there? Well, it means this. Okay, and let's put it as a definition in the dictionary. So yeah, all definitions in the dictionary, the ones that relate to physics, the critical ones, not one is defined properly in any dictionary on planet Earth. Okay, so we need to look at all these words, okay, and find out if they, what the correct definition is. In other words, by correct, I mean what the rational definition is that we can use in physics consistently, rationally, scientifically. Okay? But this guy did say something which is true, correct, and rational. Energies and fields are abstract ideas, correct. Abstract ideas can't do damage to objects. Absolutely. At least he learned something. Yeah, concepts cannot interface with objects, with things, with media, right? Mediums. That's why concepts are not part of physics, in the sense that you cannot use them as physical objects. Can't move concepts around. That's what this channel is about. Okay, here we have one fellow, and he says the following. He says, Einstein said that speed can multiply mass. Whatever that is supposed to be. Yeah, absolutely. I mean, it makes no sense, but let me tell you why it makes no sense. Because math has nothing to do with physics. And that's why the mathematicians, you'll hear very often say that, well, we cannot put our language of mathematics into the words that we use in ordinary speech, meaning physics. We cannot put it into physics. That's what they mean. Yeah, because math has nothing to do with physics. Math is a description, quantitative description of how something moves. And physics is about explaining mechanisms. So one thing has really nothing to do with the other. We do not need any math, any equations, any numbers to explain a mechanism. If I ask you, how does a car work again, you can explain, how the gas goes all the way to the engine without using any math. I don't need to know quantities. I don't need to know how much gas has to go. I don't need any of that. I just say, look, the gas moves from here to there, and it makes the engine work, and we go through the different parts of the engine. You do not need any math whatsoever. That's why math has nothing to do with physics. And that's the problem here. The problem here is that, these people say E equals MC squared. Okay, so E equals, what is that? That's a mathematical, equation. That's just a formula. And, you say, well, let me translate that into physics. And that's what this fellow is referring to. How do you multiply mass times velocity of light squared, times speed? And in physics, it makes no sense. It makes no sense to multiply speed times kilograms. Okay? Because none of those things pertain to physics. They pertain only to math. And then you can play around with the units out there in math, but don't bring any of that into physics. It has nothing to do with trying to visualize the mechanism of what that represents in mathematical terms. Okay, fellow says, again, throwing rotten tomatoes in my face, says, you cherry pick comments. You know very well and better than anyone where your hypothesis fails. Why not talk about that for an hour? Well, do I cherry pick? There is some amount of cherry picking because it's unavoidable. I mean, I get comments in Facebook, in Quora. I get comments from YouTube, from many sources, even from Patreon. So I get comments and questions from different sources. I can't handle all that in my lectures. I try to answer the ones that I think are pertinent, and in fact, I can't be accused of favoring or cherry picking in favor of some people who already understand what I'm talking about here in general. In fact, I do the opposite. I usually put comments of people who do not understand, which is really 99% of the time, or who are offended by what they hear here. They say, oh, but that's not science. You're doing semantics and blah, 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 word salad. No. I put comments usually of people who are against this channel. So in that sense, you cannot accuse me of cherry picking. But there is some amount of cherry picking because I can't put all the comments I receive. That's one issue. The other one is, usually I put comments or questions that are related to the subject matter at hand, but I cannot be accused of just favoring people who side with me. It's the opposite usually. The comments I put are people who usually are against this channel, okay, who do not subscribe or to the ideas presented by this channel. Okay, and so this fellow continues. He says, the ropes you describe without explaining evident mechanisms. I don't know what he's talking about because I explain all mechanisms. Maybe he hasn't been here long enough. Are resembling the lines of force that mathematicians describe. Yeah, but see, again, it shows this person doesn't understand. The term lines of force, the word field, none of those two words belong in physics. They have nothing to do with science. Okay? There is no physical object called a line of force. There is no physical standalone object called field. Okay? But if you think otherwise, hey, very simple. Next time when we come to the conference, you bring a line of force and a field and put it there in the middle of the room so that we know what you're talking about. Okay? Bring a line of force. Okay? Once we see it and we say, okay, now we see what you're talking about. Okay? There's no such thing as a line of force. There's no such thing as field. But ropes, hey, ropes, we can show you ropes. Just go to the hardware store. Thread, also, it's a physical object. Here's a thread, okay? It's my floss thread. I'll let you use it after I use it, okay? No problem. And I hope you see that, okay? So there's the thread, okay? So thread is a physical object, okay? That's what we're saying. That's what we're saying that light is comprised of, two twined threads. What part of that someone may not understand, I have no idea. It's straightforward. It says, you really owe this answer to many. Step up, buddy, and defend it. You are not quite rational when it comes to the issues above. Well, I don't know. Unless you tell me what you object to, what mechanism I did not explain, or what theory I did not explain, what object I presented that is irrational. Those are the things you have to criticize by. I'm not a mind reader. I don't know what's going through your tiny little brain, okay? And here is same fellow says, you say ropes don't touch, but in the case of magnetism, you contradict yourself, saying that the single strands that the jumping guy jumps when they cross have minute touch. Yeah. First of all, let me say it's a very good question, okay? It's a very good question. And the answer is that on YouTube, I say that the ropes don't touch and the threads don't touch. That's on YouTube, okay? In the book, I say something different. I say they do have a tenuous touch, a friction, okay? And I explain the context. But for the purposes of YouTube, I cannot go into all those details because it's very complex. There's a lot of people who don't understand what Rutherford backscattering is or neutron bombardment. They have no idea. So it's a little over the top for some of these people. I cannot just go in there and start talking about all these little exceptions, okay, or all these scenarios where we do introduce touch, okay? So for the purposes of YouTube only, we say they don't touch, and that simplifies it enormously. Your question is very well taken. It's good. It's a good question. We have addressed it, but it's in the book, and I will not touch upon that in YouTube because it's just too complex. You have to go through many different scenarios to answer your question. Okay, so do they touch? In the book that says yes. Okay, so you would have to read the book to understand what we're referring to, under what circumstances we introduce the word touch. And for that, you need to define the word touch, which no one has ever defined. I'm sure you don't understand what the word touch means, so even you don't understand what you're asking. And again, we have to define the word touch so that everybody can use it rationally, consistently, scientifically. So we have defined the word touch, and that's where we started. Okay? Before you can cut across, hopefully when at some point they mean, we call that touch, right? So what does touch mean? That's where we had to start. Okay, same fellow, he continues, he says, also the atoms which are connected to all atoms that are at the extremities of the magnet are also connected by a single magnetic strand, the rope that guy jumps, okay? So he's saying there's a single strand, comes out of the atoms, and it also comes out of the molecules, it comes out of the rope. Okay, we have two theories there, one where it comes out of the atom, the other one comes out of the rope. Okay, there's two theories for how the thread comes out. Okay, so you say that the atoms are connected to all atoms, also spin single magnetic threads at the extremities of the magnet. You are being irrational, Bill. Well, not quite, and I'll show you that in a second. What is the mechanism that turns the thread in the rope and turns the rope into single threads? Okay, so let's answer this gentleman, and it's not a full answer, but I just want you to get the hang of it a little bit. Here it is, okay, and I want you to watch this. It's going to show you how the thread comes out of a spinning serpentine. We have two atoms, and the threads come out from the rope here. Okay, in this case, it's the theory of the rope. Now you have a whole bunch of atoms lined up. We call that a serpentine. They're all merged with each other, and as they spin, the threads come out. Okay, the threads are going to come out of here, and current is the spinning of the entire serpentine, and you can see that matches what we have out there. What is the field, the so-called field? It's a bunch of these threads that come out of, in this case, we've did it with the rope, but they also come out of the atoms, maybe both, maybe one or the other, and that's what forms this wall of threads that we call the field. Okay, so it's a wall of threads, okay, that essentially is coming out of the same atoms of which that are made of these threads. And in the case of the rope, where we talk about magnetism, the magnetic field being threads that come out of the rope, we have that when they spin, the two threads come out from the rope. In the case of the atoms, they're all bound together, they're all merged together. When the whole serpentine, the whole series of merged atoms, really molecules, when they spin the threads that make up part of the atom, and they spin around. So that's where they come from. Are they still connected? Yes. In the case of atoms, in the case of merged atoms or merged molecules, actually, they're already merged. So the thread comes out of the atoms. Okay? And they come out and they spin because the atoms are spinning in situ at great speeds. And that throws the thread out. Does that mean that they get disconnected or that the rope is dead and it's ripped or whatever? No, they come out, they spin, and when the magnetism stops, they go back to where they were. That's more or less, in general terms, what we're trying to explain here. Again, all this is in detail in the book. That's all I can tell you. That's not a cue for you to buy the book. I'm just saying that we do have it explained in the book. It's not like I'm improvising here and say, well, let's see, how am I going to answer the question? No, we've already answered those questions in the book, but you got to read the book if you want to understand the details of all those processes. Okay, here it says the same fellow, I think, I don't see how an atom can form in this model, nor do I see how it can keep together. If it was all intangible ropes, why do they form clusters like atoms and not just go through each other? And if light is going through the ropes, why not through the ropes? It's the rope itself that spins in situ, it torques in situ, okay? Why then, when they torque, it travels in a specific direction? No, it travels in two opposite directions. In other words, the ends of the rope cause a thump on the atoms at the opposite ends. That's light. The thump into the atom. Why? Because the atom is made of those same ropes. So this issue of how did the atoms connect, there is no connection to the rope, right? There is no connection. It's not bound or pasted on or linked or attached. No, the rope becomes the atom. Okay, one strand becomes the proton star, and the other one goes around and forms the electron shell. When you have gazillions of threads coming from every atom in the universe, you can see our atom is a bundle that is a star with gazillions of threads, crisscrossing in the center of the atom, hydrogen atom to make it simple. And that's covered by a ball, a membrane, a balloon made of threads, which is the thread that curved around from every atom in the universe. So every atom in the universe is made from the thread that comes from every atom in the universe. Okay? Here's the construction. Okay? So I don't know if it's beyond your capabilities, but there it is. You can see the electric thread moves through the center. It's going to form the proton, and then the magnetic thread loops around and forms the shell, or the membrane, if you want to call it, or whatever. And there you see, that's our atom. So the atom, and there you see also the ropes end at the electron shell. What continues is the electric thread. So the electric thread goes through the center. All the electric threads are going to form the proton star, and what encapsulates this whole thing is the magnetic threads from every atom in the universe that form this balloon, this shell, this membrane that encapsulates the proton star. And when that atom expands and contracts doing its quantum jump, it torques the rope. Very simple, straightforward. This is kindergarten stuff, hopefully, for everybody. Okay, we're not talking about stuff that's out of this world. Mother Nature runs a very simple universe when it comes to physics. The math, that's complicated. You got to take calculus and linear algebra, all that stuff, which I had to take in college. Has nothing to do with physics. None of that has anything to do with what Mother Nature uses. The language of Mother Nature, the language of physics, is not what Galileo said. Galileo said math is the language of the universe. Absolutely not, Galileo. Not at all. The language of the universe is illustration. We illustrate because Mother Nature never went to school. She doesn't, and Father Universe neither. They never studied math. What they do is move objects, one atom to another position or another location from frame to frame in a universal movie. Okay, so every atom just moves to a different location. That's all they do every day. They don't need any math for that. They don't need to understand math. They don't need to know numbers. They don't need to know relations between the circumference and the diameter. They don't need to do any. They don't make those relations. All they do is move atoms from one place to another. That's the universe out there. Okay, that's physics. You can explain mechanism, how Mother Nature, Father Universe, how they run the universe. Illustration is the language of physics. Okay, a fellow here says, I never said light was going through obstacles, okay? Because we were talking about, the fact that light turns around corners. We were talking about the slit experiment specifically where we shine a light on a needle, not a slit, but a needle, okay? And what happens is, we have these fringes on behind the needle. We don't need the slits. We can do it with a needle. And the problem there is, how do you get particles to turn a corner? That's the issue. And this is the second or third time now this fellow doesn't answer that question. And he says, I never said light was going through obstacles. Okay? No, he did not say that. I said that, and I put those words in his mouth. I want to clarify that. It was me who put those words in his mouth. Why? Because he proposes particles, and you cannot produce that Poisson spot. There, you see there, take the Poisson spot experiment. Where did I say light was going through? Right, he did not say that. I said that. I said that the only way he can explain it with particles is this way. If he goes right through the needle with particles, then we can make, if we can achieve this, which is unachievable, by the way, but assuming we could achieve that, that's the only way we can explain how that little tiny spot is made in the center, called the Poisson spot, in the center of that image, right, on the right, the pink one there. Okay, so the only way you can do it with particles is going straight. Okay, that's if you could achieve it, which is impossible anyways. What does this guy propose? Well, this fellow proposes something else. He says, you know, the particles that create that little spot in there are the ones that turn the corner in the circular needle, you know, because the edges of the needle are curved. Well, this guy doesn't know the first thing about physics. I guess he's never tried this anywhere in his life, you know, like the particles are going to bounce from the edges of that needle and go outwards like I showed there with the reddish particles. They're going to go outwards, not inwards. And this guy just has them coming inward, and he says that this is due to the law of reflection, whatever that is. You know, we have no idea what this law of reflection that he was taught at the monastery is. Yeah, so the only way, so I did put the words in his mouth because I'm saying the only way he can explain with particles is this way. If the particles go straight right through the needle, then he can maybe somehow explain how that little spot was made there. If instead we go with his irrationality, which is hitting the edge of the needle and bouncing inwards, well, that process he's going to have to explain. You know, they don't bounce inwards, they bounce outwards. So where did he get the idea that the particles, discrete particles, that are going to go inwards? You know, they hit the edges of the obstacle there and go inwards? No way. And you can do it with a rope. There you can see the ropes in that middle, or the one in the center there that I put in there. You see the ropes coming to the edge of the obstacle. In this case, we're going to say that's the needle, right? Portion of the needle. And it touches, in other words, it is connected to the atom that's right there at the edge of the needle, on both ends of the needle, at both extremes of the needle. And from there, another rope that is connected from that atom to the wall, right, is the one that makes the little spot there. And how does that work? Well, you have all these ropes coming from the edge of the needle or the spot or whatever you put there as an obstacle, and they're all synchronized in such a way they have to be at a precise distance, right, so that all the ropes are matching. In other words, that the the threads of the rope match. In other words, green has to match with green and orange has to match with orange for there to be a spot. If you move that a little differently, you won't get a Poisson spot. You will only get it if all the ropes match. That, you know, they're coming from the same source, by the way. That's light there. That's taking the torsions to the wall. And what you're staring at there is that all the ropes are synchronized. They're all at the same, the last link in all these ropes matches. Okay, they're not offset by half a link. That's the point. That's how you make that little spot there. And you can't do it with waves, even though wave is the proper mechanism. Wave is the wrong object. There is no such thing as a wave, a transverse wave. What those are just vectors. Those are mathematical vectors. They have no place in science, let alone in physics. Okay, so we're talking about a physical object called a thread, not a field. Okay, there is no such thing as a field or as a vector, not in physics. That's mathematics. Okay, and so this fellow says the point in the middle comes from a few inward reflected light rays. Yeah, that's what we need for you to explain. Okay, you need to explain, because he's talking about reflection. Reflection is bouncing. Bouncing, it's going to bounce outwards, not inwards. So this is what this fellow doesn't understand, and this is the third time now, and he says he's a rational individual. He's not. Okay, here, let me show you what happens when you throw a ball against a tree. Let's see if it bounces inwards. Okay, here it is. Okay, hits, where does it go? Does it go inwards like that? Try it at home. Find a tree, throw a ball to the edge of the tree, and you'll find that this is what happens. Outwards. That's what a ball will do. It will never bounce inwards. So that's the process we want you to explain. Okay, and this fella, he says it's rational. It's a rational mechanism that he's proposing. No, it's the most idiotic thing that you could propose. Okay, throw a ball against the edge of a tree and see if it bounces inwards. Film it and bring it to us. We want to see that. Okay, don't cheat. Okay, so here it is. He said the law of reflection is not just a mathematical law. Yeah. That's whatever it is. Yeah, the law part belongs to math. The reflection part, that's a physical issue. So again, law of reflection means they're going to try to merge math with physics. That can never happen. They have laws in mathematics. We have no laws in physics. Okay, law means we have an equation or something. Okay? There is no such thing as a law in physics or in science for that matter. Laws belong completely to mathematics. Law means that they convinced you of something, and that you follow the law, you believe it, you know it, meaning you have a strong belief. That's what knowledge means. Okay, so but anyways, that's just a description to say the law of reflection. What does he mean by that? I mean, what does that mean? The important thing is that light reflects. Yeah, reflects means it bounces, and when you throw a ball against the edge of a needle, against the edge of a tree, telephone post, whatever you want to use there as an obstacle, it'll bounce outwards, never inwards. Okay, so what you need to explain, let's see if you got it, Bean Brain, okay? Inwards, show us how the ball comes inwards. Okay, that's the issue. Okay, so I don't know how else to explain it. This is the third time now, guy. As for bending around corners as usual, you don't listen. Okay, I'm not listening, okay? I said apparent bending. Okay, that's irrelevant. But light doesn't bend, irrelevant. Okay, it's still reflected even if you don't understand how. That's what we want to understand. We want to understand how, if you can explain how. To show us how a ball bounces inwards when you throw it against the edge of a tree. That's what we need for you to explain. And don't tell me the law of reflection. You know nothing about law of reflection. Okay? So, I don't know, you got all these people there, they all think they're experts in math and physics, especially in physics, and they haven't taken kindergarten physics, but they know it all. Okay, hold it. Okay, so here we have this fellow, and he ends his dissertation, and this is where you need a beer. He says, as for light particles, he's going to propose particles, right? Light does somewhat behave as particles, but I don't believe they are the kind of particles many believe in. Particles is particles is particles. I mean, we're talking about corpuscles. You want to make them round, you want to make them cubic, triangular, we don't care. Particles is particles is particles. Okay, so don't tell me that they're not the particles that everybody thinks. Show us your particle. What kind of particles are you inventing? Are they round? Are they cubic? Are they, what are they, tesseract-like? I don't know. You're the guy who's giving the presentation. You got to tell. You can't say they're particles, but they're not the particles that everybody thinks about. Well, I don't know what other particles there are. Particles are always round things. If they're not round, then you have to say, well, they're cubic or they're T-shaped or whatever. You have to tell us when you talk about particles. And they don't understand that the objects is where they all fail. They all fail in the objects. That's why they propose ether. That's why they propose particles, because they say, well, particles, you know what I mean, and they continue. No, you got to tell us what these particles are, what encapsulates them, what is the backdrop, is it space, what gives shape to each particle. You got to go through all that whole process. Spend 2 years on your assumptions and 2 seconds on your irrelevant theory, because for sure it's irrelevant. They are not spherical beads. So he tells us what it ain't. He never tells us what it is. Just like the ether is and all these other people. They tell us what it ain't, never what it is. We need to know what it is. Don't tell us that we're wrong. We know we're wrong. We concede. I concede. I don't know, okay? I concede. You tell us. You're the guy giving the presentation for ether, for plasma, For particles, you're the guy who has to tell us what you mean by those words. And I don't know how to get that across to these people. They always skip that step. They say, well, you got it wrong, Bill. Yeah, no, I always have it wrong. Just tell us what is right. And then they tell you, to add on, and they say, well, the reason I can't tell, I've never seen the ether. I've never seen, these particles. I don't have good eyesight. I don't know how to draw very well. They come up with all this idiocy, this nonsense. You're giving the presentation. You have to visualize it. I don't care if you saw them or not. You have to visualize it and make them visible for us so we know what's on your mind. We need to look inside your minds to see what mechanism you propose. We can't get to the law of reflection until we know what you mean by particle. And this guy hasn't told us what he means by particle. He said, well, you know what a particle is, but it's not the particle everybody else has out there. It's a different kind of particle. And so we have no idea what he's talking about. And then he said the particles don't have a specific structure or size. So they don't have size. A particle that doesn't have size, that's great, and they don't have structure, and that's great too. I mean, no structure or size, but it's a particle. So again, he's moving concepts around. He's saying it's a nothing that moves around. It's a zero-dimensional nothing, no size, no shape, no nothing, and that's what I'm going to do my magic with. Yeah, and then he adds, he says, you won't find a more rational explanation for light on YouTube. My poor God. Are these people for real? I mean, come on. Okay, so I think it's the same guy. He continues, he says, light interference does not exist. Okay? Ever notice how two beams of light do not affect each other? Yeah, he's totally right there. You cross two laser pointers or two flashlights, and, there are no particles jumping around. Like if you took two shower caps, shower sprayers, and you move around or you take two hoses of water, right? And you move them across, you'll find, water molecules jumping out of there. They're going to hit each other. They don't go through each other. They bounce. Okay, so if you take two hoses and go like that, cross them, you will find that water does bounce. Water hits water. Molecule hits molecule. That doesn't happen with light. You can take two flashlights or two laser pointers, and they will not interfere. Even though there's I can't remember, Burke. Look up Burke, and these people say they've proven that particles of light hit particles of light, and then they create what? Virtual particles. So they introduced this virtual particle for their paper to explain how particles of light actually bounce against particles of light. And they do it with all virtual particles, which is an idiotic particle invented by quantum to explain the unexplainable. Okay? But other than that, for rational people, other than Burke and his group, light does not interfere with light. Okay? They go right through each other. So he asks, ever notice how, well, he says, they just go through each other. In that case, how could light interfere with itself? It's illogical. Well, no, it ain't. It's just that you never were smart enough to figure it out, what the magic trick is. Yeah, it's like you go see the magician cut the lady in half, and the guy says, well, you cannot explain that. And the mathematician says, yeah, sure, I can explain it. In this universe, the lady comes out in one piece, but in another universe, she was cut in half, and they took her to the hospital or to the morgue. Okay, so let's explain to this guy how we do it with a rope model, how light does interfere constructively and destructively with ropes. You cannot explain this either with waves, okay, transverse waves, because wave is not a physical object. That's why you cannot explain it with waves. What is a wave made of? Two fields. Fields are not physical object. Fields are a bunch of vectors, so that's the end of the wave. There is no such thing as a wave, a transverse wave. Okay, the famous, perpendicular electric magnetic wave. No such monster in physics. That's irrationality of mathematics. Okay, so how do we do it here? And you do have to pay attention now. We're going to go very slowly here because not everybody can visualize what I'm going to show you here. Okay, so let's Let's go slowly. Okay, here it is. What do we show on the top? On the top, we see two ropes converging upon a black atom. Okay, that's the one on the top on the upper left. Okay, and you can see that the atom is not pumping very wide, very big. It's just very tiny, right? It's below the visible range. Why is that so? Well, because the frequency on the ropes, the number of links, and the number of the fact that the ropes are not torquing very fast. That's essentially it. Okay, so it doesn't matter whether the ropes match, in other words, red with red or blue with blue, versus not match, red with blue and blue with red, because the frequency is very low, and so the atom is not pumping very widely. Okay, and so that atom sends a signal through a rope to an atom in your eye. That's the one on the right. The black one on the right is the atom in your eye. Okay, so you can see it's low frequency, it's below the frequency, the visible range, and that's why you see a shadow or a dark spot or whatever. You don't see any light. Okay, that's what happens before turning on the light. Now we're going to turn the light on. What does that mean? Turning the light on means you're going to increase the frequency on the rope. That means now there are more, the torsion has increased. The rope is spinning much faster now. And what happens is now you have more links per unit length. Now it brings it into the visible range. What does that mean? It means the atom is now pumping much higher, okay, much wider, and sends that signal to your eye with a higher frequency. You have more links per unit length, okay? That's what you have there. That's the bright band. Why don't we see the dark band? Why is it dark? Well, it's the same signal, but it's a parallel signal, and that signal on another rope, okay, another set of ropes. And what happens here, they're not matched, they're not synchronized. You have red with blue and blue with red. And so while one rope is trying to make the atom expand, the other one does not allow it. The other one forces it to contract. So the atom is not expanding as much as in the bright band. It just expands a little bit, and that's below the visible range. And that's the signal it sends to the atom on the right, black, which is in your eye. Okay? So what we're saying here is the bright bands that we see on the wall are because you have higher frequency, meaning more links per unit length. And the dark band means it's below the visible range because one rope is offset by half a length from the other rope. And so while one is telling the atom to expand, the other one is telling it to contract. And so the atom is essentially pumping at the same speed it was before. That's in general the mechanism that we propose, okay? And here we're going to see those ropes head on, okay? So now we're staring directly at the rope as it comes into your eye. In the case that you have above, the one on the top, right? Both ropes are red with red and blue with blue. So the torsion is enhanced and we have constructive interference. What happens on the bottom? Well, you can see that red does not match with blue and blue does not match with red. And what happens is, one is telling the atom to expand, the other one's telling it to contract. And so that's the difference in what happens to the atom that's in your eye. So in one case, the atom in your eye is expanding and contracting. And again, we do this at the atomic level. We don't explain it at the molecular level because it's a much more complicated process. And also, we're going to be talking about cells taking the signal all the way to your brain and that kind of thing. We're not going to get into that. We just want to show you the mechanism, the general mechanism of physics. We're saying that in one case, the atom expands much wider, and in the other, it doesn't. Okay? And that's the difference between constructive interference on the top and destructive interference on the bottom. So yes, we can explain it with a mechanism, a physical mechanism, and it gives us more confidence that we're talking about a rope A rope can be a mediator for light. Particles cannot, and waves cannot. What they've been using for the last 400 years, since the days of Robert Hooke, who came up with the wave nature of light first. In his book Micrographia, 1665, he wrote about it because he studied it through the microscope, and he says, I see some waves where I see light, and I think light is some kind of wave phenomena. And in that sense, he was at least right. It was a good start. Okay, yeah, wave phenomena, but then they mathematized it and came up with, you have Maxwell and so on, primarily Maxwell, saying that, giving numbers to all these things when we didn't need numbers at all. We just needed to see the object. What object are you talking about? And Maxwell just said, oh, a bunch of vectors. Well, that's not an object. Okay, we had another issue, also kind of important. Okay, here it is, and I showed this, that a magnetic field sucks smoke. What I didn't tell the people, and I did that purposely, is that it's a rotating magnetic field. And I thought that was irrelevant. I just said that a magnetic field attracts smoke. And the guys said, well, there's something going on there. Yeah, something is going on there. I didn't want to tell you about it because that was irrelevant to my lecture. The point that I was trying to make is that a magnetic field has a way of affecting smoke. Whether it rotates, stands on its head, or jumps around, we don't care. We're just saying that a magnetic field has the ability to affect smoke, like you see there. Okay, and so all these guys, went up in arms. They didn't like my my pictorial representation of how a magnetic field sucks smoke. So they came up and said the following: said, magnetic field does not attract smoke. And the other fellow says, that, referring to the magnetic field attracting smoke, right? That obviously has nothing to do with magnetism. So they don't believe that magnetic field has any way of affecting, smoke. So what is smoke? Well, what is smoke is a bunch of molecules. Smoke is a gas. It's just a bunch of molecules there, and we're saying that a magnetic field, which you cannot see, right? Because actually it's a bunch of threads that make up the magnetic field. Those threads are spinning at great speeds, and it's those threads, intangible threads, right, that somehow come in contact with the molecules of smoke, of this gas. And they say it's impossible. A magnetic field cannot touch smoke, cannot touch gas. And so I'm just going to make that case right now. First thing we have to make sure is that we understand that, yeah, exactly, field is a concept. So you cannot say that a field touches smoke or does something to smoke. Fields cannot. Field is a concept. And no, I'm not doing word salad. I'm not doing semantics. It's called science. It's called physics. You need to use the right language. You cannot use the word lines of force, and you cannot use the word field to talk about physical interaction. Those are not physical objects. They are concepts, and anyone who uses a concept to move a physical object is known as an irrational individual. So anyone using the word field in physics or the word line of force in physics is an irrational individual. He has not understood the language of physics. Okay? And yeah, you call it semantics, you call it word salad, whatever you want to call it. It's called science. It's called physics. Field is a concept, so you cannot use it as an object. Concepts have no way of interacting with objects. It is irrational to say that a field touches the molecules that comprise smoke. No, field cannot, because field, first of all, is infinite. Remember, the mathematical field extends beyond space-time. Every field does. Magnetic field, electric field, gravitational field, all extend infinitely. So you cannot say the field is an infinite thing affects this thing right here, right in front of me. Now, if it's infinite, you cannot say. You got to look at the shape of this field, and of course, a field has no shape because it's a concept. See how easy it was? You cannot say that love moves mountains. Okay. A thread, on the other hand, here's a thread again. My floss thread. I will let you use it afterwards. Don't worry. Is an object. That's a thing. Okay? That's a thing. Being objects, these threads have the ability to interact with matter under certain circumstances, and that's what we're going show right now very quickly. I'm going to run through these. You can look at them later on, so I'm just going to run them relatively quickly. Here's the first one. These are all papers, published papers, most of them at least. Okay, here it is. This one says rotating magnetic field on hydrogen production and water. So this one says, this paper, if you can look it up there, you can read it, says that a rotating magnetic field, meaning the rotating threads, because there's no such thing as a field, okay, rotating threads can affect water and hydrogen. Okay, so that's what this paper is about. You can look it up. Here's another one, just so you can see. Okay, this one says that wind generated, et cetera, et cetera. Well, essentially, they're saying that a magnetic field, rotating magnetic field, essentially, right? I'm not going to repeat that constantly, but the threads, rotating threads, affect wind, affect air. Okay, what is air? It's a gas. So if it affects a gas such as air, well, probably it affects smoke, which is another gas. Why not? Here's another one, says the same thing, says that a magnetic field changes wind. Okay, if it interacts with wind, it affects wind, and wind is air really is a gas. Okay, wind is moving air. So yeah, it does affect, it changes, it interacts with the molecules. Okay, here's another one, and again, you can look these up later on. Okay, Earth's magnetic field extends several tens of thousands of kilometers into space. What does it do? It protects us against the solar wind. What is the solar wind? Is it some kind of air, molecules, whatever? Well, it's a stream of charged particles. That's how they define it. In other words, we're talking about particles, probably atoms, okay? Maybe molecules, some molecule. The point is you have a magnetic field that interacts with molecules, with atoms. That's the point of that one. Okay? So yes, magnetic fields, as they're known, meaning the threads that are spinning around in that region, they do interact with molecules and with atoms. That's what I'm trying to say here. Here's another one. This one talks about affecting gases of a galaxy. Okay, so you can look that one up as well, and you'll find out that a magnetic field has the ability to affect gases in galactic gases at the galactic level. So it's not like, I've invented anything new. This is all in the literature, okay? So to say that a magnetic field has no way of affecting smoke, well, think again, okay? Now, that doesn't mean that what this other fellow said is completely out of mind, out of body. It could be that the field, the threads that are moving in there, swinging around, they're moving the air first, and by removing the air, then you have smoke filling in that region. But I'm going to address that in a second, and you'll see why that's not completely rational, what this fellow is saying, but let me get to it. Here's another one. This one says that magnetic field, right? The threads there, the physical threads, right? They have ability to move a coil around. In fact, Faraday discovered that a long time ago. Okay, so he was astounded by that. Okay, but yeah, field can interact with matter. Not all the matter that you would think in the way you think, but it does have ability of affecting matter, and especially gases. So for people to say, well, a magnetic field cannot affect a gas. Yes, it can. Okay, and so here's the other issue that I raised for this. If you look at Cora, tornadoes, right? And it says, pick up debris from the center and throw it outwards, ripping apart structures and scattering them. And another fellow says, tornadoes do not suck. There is no way you can be sucked into a tornado. What's the issue here? Well, if you saw the smoke going to the center of that rotating magnetic field, meaning the rotating threads that are in there moving around, well, in the same way, I can play devil's advocate and say, well, why doesn't that kick the particles of smoke outwards? Why does it suck it in? I mean, after all, they're particles. This thing is swinging, right? And like a tornado, I can just as well say that the effect that we should predict, right, is that all these particles are being hit like baseball, like a bat hitting baseball out of the ballpark, So they're swinging around at great speeds. They should be hitting the particles outwards. Why did they suck them inwards? Okay, so that's the other thing you would have to explain what the mechanism is there. Okay, and that's where we take this fellow next. He says the following, says that obviously has nothing to do with magnetism, and he continues, says, and everything to do with fluid mechanics. Like if he knew what fluid mechanics was all about, okay? There's not one mathematician on earth that knows anything at all about fluid mechanics because they've never done it with objects. They've always done it with equations, okay? So they don't know the physics of fluid mechanics, and I'll get to that in a second now. You'll see why they have no clue whatsoever. And here you see it. He says, like a vacuum cleaner. See, a lot of these people, especially the flat earthers, right? They have this notion that if you produce a vacuum, right, particles immediately rush in. And that's the notion all these people have in their tiny little brains between their ears. You produce a vacuum and particles rush in. Okay, what's the mechanism? How does vacuum pull on a particle, or how does, when you create a vacuum, what pushes the particles into that space? I need to know the mechanism. I want you to tell me why a molecule. Don't tell me about, the whole shebang. I just want one molecule. Okay, we produce a vacuum. Nothing there. Perfect vacuum, if you want. Why does that molecule move into that space? What pulls it in there? Why doesn't it go in the other way? Okay, so that's what we're going to talk about in a second. I'm going to give you a good example. It's going to blow them away. Clearly, there is some device rotating there on the right at a very high rate. Yeah, it was the rotating magnetic field. I didn't say that it was rotating. I specifically left that out. I just wanted to make a point that a magnetic field, right, meaning the threads that are moving in there, they have the power, the authority to interact with matter, with molecules of smoke. Okay, and so he says there. This is where we're going to get into it in a second. Here it says there are gaps or holes within it for the air to get sucked in. He's going to talk about vacuuming. He's talking about sucked in, and he says so the smoke drifts into the zone of lower pressure. Why? What's pulling from the vacuum this molecule that's now moving, drifting, into the region of lower pressure? Why? What causes it to go there? See, these people just say things. They say, "Oh, I'm an expert in what do you call it? Fluid dynamics, etc." They know nothing. They know absolutely nothing about physics. They just read something about fluid dynamics and say, well, we've observed that particles move in there. Yeah, they move in there. Why? What's causing it to move in there? Why don't you tell me the mechanism? And I'll give you an example here. Here's the example, okay? We have the Earth. And for those of you who are not flat earthers, the Earth is covered with air. That's what we breathe here, and there's this layer of air that goes up several kilometers up in the sky, right? What continues is vacuum. At some point, it gets less dense. At some point, somewhere between the two stars, between the Sun and Alpha Centauri, there's much less air there. And if we talk about between two galaxies, well, there's almost no air whatsoever. So the farther out you go from the Earth, the less air you find, right? We find what we call vacuum. And let's just talk about perfect vacuum just for the sake of conversation. Let's assume that at some distance from the Earth, there's perfect vacuum, okay? So here it is, the picture, okay? We have vacuum up there, lower density, right? And higher density is right close to the Earth, to the surface of the Earth. Why doesn't the air molecule leave the Earth and float into the vacuum if the vacuum pulls particles, if all molecules of air drift into the region of vacuum? Here you have a vacuum. Why doesn't the air leave the Earth? Okay, that's the question you have to answer. And these people just say, oh, it's the, fluid flow, the flow fluid, and they talk about all this nonsense that they just learned by rote. They will not tell you the mechanism because not a single mathematician on earth can tell you the mechanism. And what they say here, well, the reason it doesn't leave the earth is because of gravity. Yeah, what is gravity? What's pulling on each molecule of air or atom of air or O2 or whatever you want to call it, I don't care. What's pulling on it towards the earth? Why doesn't it leave to the vacuum where you say that all particles tend to float towards? Okay? So that's the question, the $1,000,000 question in your hand. You're supposed to answer that question. Okay? And final issue here, okay, and here it is, magnet. I showed that you can see that the iron filings, these nuggets are collected one by one. You can say this is in slow motion. That's why we can see it. And you can see that the iron filings, once the magnet is put into the water, into that region, suddenly they all start going towards the magnet little by little. If we did this in real time, like out here, well, what you would see is that suddenly, you would see this. Suddenly all the nuggets fall around the atom, the magnet, so we would not be able to see the process. Here you can see the process. It's a very slow process, and you can see something is moving around in that region we call field. We call them the threads that are moving around, and those threads are pulling one nugget at a time. Okay? So what does this fellow say? Okay, so we have an explanation. We're saying there's a physical thread that's swinging around many threads, gazillions of threads. They're going like that, and they're pulling one nugget at a time. And of course, those threads have their origin in the magnet itself. So what happens is, farther the distance, the fewer threads you have, intervening in the process, and at some point, the nuggets are not picked up because the magnet is simply too far away. You would have to move the magnet closer to those nuggets so that some of the threads are closer and you can pick them up and put them next to the magnet. Okay, so what does this fellow say? So we have a process, we have a mechanism. What does this fellow say? Iron can be magnetized by a magnet. Hey, no kidding. I'm glad you learned that. Okay, so how do you magnetize it? I mean, not how. What is the process? What does a magnet do to magnetize iron? That's what you need to find. And they give you this general explanation, say, well, the domains are aligned. Yeah, what's affecting the domains? What physical entity is in contact with the domains? Unless you can tell me that, you know nothing about magnetization. You have to identify the objects, the things that are invisible and intangible to humans. So what you're seeing is a chain reaction of magnetization of those iron filings. Yeah, you haven't explained anything. Okay, all you're saying they're magnetized. Yeah, how did they get magnetized? What touched them? Okay, whatever is making those fillings fall in is running out of steam because it eventually grinds to a halt. Yeah, because of distance. But I'm glad he says whatever. Yeah, don't tell me whatever. You need to tell us the whatever is. What is that whatever? That's what you got to identify. Unless you identify the objects, you're not doing physics. You're doing some nonsense there that you learned by rote. You're just repeating, regurgitating what they taught you by rote. No, you have to tell me what that whatever is. And that's what they never tell you. They never deal with objects. And when you put them there, you say, oh, you're doing word salad, Bill, you're doing semantics. No, we need to identify the objects in physics. Without objects, you cannot do physics. So if we're perpetual jump ropes responsible, why do they run out of juice? Distance. Very simple. It's straightforward. I mean, and I've said that several times in many of my videos, but maybe this guy hasn't watched them. Do they get tangled up or something? No, they don't get tangled. There's no tangling between ropes or threads. Really, the threads in this case is the issue. Magnetism works with threads. A lot of people confuse rope with threads. Threads are not ropes. Ropes are not threads. You have to keep those separate. Ropes are used for gravity. Threads are used for magnetism. Keep those separated. Never mix them. Okay? No, it's because the influence. Oh, we have the influence now. The whatevers and the influences of the magnet. Yeah, how does it influence? We need to know the object. Tell me the physical object and what it looks like. and how it comes in contact with a magnet to magnetize it. That's what we need to know, that level of detail. Otherwise, you know nothing about physics or about magnetization. So don't boast about your ignorance, okay, especially on this channel. Okay? So he continues, has spread to its maximum extent throughout the filings, and all these new magnets have found equilibrium with each other. Yeah, he's just describing stuff. He hasn't explained absolutely anything. In order to explain, you need physical objects because you're explaining a mechanism, a cause. That's what we're looking at. So you need to tell us what came in contact with the iron filing to magnetize it. When the Earth moves around, you know, the magnetic field of the Earth, you know, all these threads that are moving around, but they call them field, okay? We'll use the word field if you want. How does it magnetize lodestone, for example? You know, you find a piece of lodestone that was made by the Earth's magnetic field. How did it do that? What came in contact with the rock that we call, that piece of iron we call lodestone that is now magnetized? So you have to identify the physical objects, and it's very hard to understand that for people to understand that. You can't do physics without objects. Okay, let's move on to our subject of today. A little late, but I'll cover it. Okay, here it goes. We started by talking the other day, or the last couple of weeks, we've been talking about light curving around obstacles, right? And we saw it in the gravitational lensing. We saw it in the slit experiment, you know. Actually, curving, there's two mechanisms out there. One is that it hits the side of the slit, okay? And the other one is that it curves around the needle. And we talked about curving around the needle. It doesn't curve inwards. It curves outwards. It hits and bounces outwards. Never does a ball bounce inwards. That's the problem with people using the particle hypothesis. And then, so what they do is they make that particle hit the edge of the frame. Okay, and here it is, okay? This is first the wave, and what Thomas Young discovered 1802, 1803 is that the what he called the wave nature of light. He says when he's shown it through two slits, he produced a bunch of fringes. He expected to see just two slits, just light going through each slit, and that's not what happened. There was an interference pattern. The dark ones are destructive interference, the light ones are constructive interference. Okay, that was his conclusion, and it's pretty much on the money. What's the problem? The problem is that when you do it with particles, okay, with waves, you can talk about interference. With particles, you cannot. Okay, and that's the issue. The issue, the way they fixed it, the mathematicians, and by the way, this is where the whole discussion was between Niels Bohr and Einstein in 1926 at the Solvay conference, the fifth Solvay conference. And so they were talking about this. They said, look, when the source throws a particle, you know, photon, it hits the slit and it's going to move it. So the problem there is that according to the Heisenberg uncertainty principle, what you have is that you don't know the exact position, and you cannot know both the position and the momentum of the particle, because the slit itself is being hit by something and it's going to move a tiny amount, obviously. But see, this is the way they had them hit the edge and coming inwards. Okay, you cannot do that if you remove, the slits. See, this is okay with you can get away with a little bit of this by saying, okay, it hits the edge of the slit, the frame. Now let's replace the slit, and that's why we do it with a needle instead. Here's the needle, and we're going to remove the slit. We're going to replace it with a needle. And here's the slit. It hits the edge. That's what we showed just a minute ago. Okay, but now we're going to remove the slit. We're going to put a needle in the center, and it turns out that you can produce, with a needle there, seen from above. If you do it with particles, it's going to continue outwards or bounce outwards. It's not going to bounce inwards. That's the issue. And that's the issue this other fellow has not been able to explain after 3 tries. Okay, we need to know how he's going to produce it physically. How after hitting the edge comes inwards instead of outwards. Our experience is outwards. Okay, So that's why we used a needle. And now here's my needle experiment, which I did a few years ago. And here you will see the setup. Very simple setup. You can do it at home. You just put a laser pointer. You point it at a needle that's there stuck to a cork. Okay, when you go to the end of the wall, okay, what do you find? You find the fringes. Okay, that's what you will see, something similar to that. Okay, you can see the fringes there. So it's produced by a needle. So you do not need slits. I don't know why, even to this day, in every university on the planet, every school where they teach the slit experiment, they do it with a slit. We don't need slits. In fact, slits confuses people because, again, like Einstein and Bohr, they thought it was the photon is bouncing against the frame of the slit. But once we remove that, just leave the needle in the center, now what does it bounce against? You know, now how does it turn the corner? And that's where the problem is. They will never be able to explain that, okay, rationally. And that's the problem with this other fellow who said, oh, I can explain it with particles, but I don't know what the particles look like. They're not round, they're not cubic, they're not triangular. I don't know what they are. He just told us what they ain't. You know, how do you define a horse? Well, it's not a buffalo, it's not an elephant, it's not a shark. So he goes through all these knots. It's not this, not that, not the other. No, we don't want to know what it's not. We want to know what it is. And so this is how they define things, by saying it's not. And you're wrong, Bill. You're always wrong, Bill. Okay, so here it is. Here's our mechanism. The ropes from every atom in the flashlight or laser pointer are already connected to every atom in the needle that makes up the needle, which is connected to every atom on the wall. Okay, so they're all connected by, every atom is connected to every atom in the universe. Okay, so what happens when the light is turned off? The frequency is too low; it's below the visible range, so we don't see any pattern on the wall, on the screen. What happens when we turn the flashlight on? Well, now suddenly we increase the frequency on every rope. Why? Because the atoms in the flashlight are pumping at a faster rate. That's what you did when you turned the light on. Now the atoms are pumping faster. They transfer, or they relay that higher torsion, that higher rate, to the atoms at the edge of the needle, really to every atom in the needle for that matter, but the ones we're concerned about are the ones at the edge. And from there, what happens is the atoms in the needle relay the signal to the atoms on the wall to which they were attached even before you began your experiment. And so what happens is you see this situation. That's why we see fringes, and where the ropes are in sync. In other words, when red matches red and blue matches blue, then you have constructive interference. When they're half link apart from each other, you have red with blue and blue with red, you have destructive interference, and that's why we see all these fringes. Very simple mechanism. No waves, no particles, it's just ropes, because that's the mediator of light. It's a physical mediator. A rope is a physical mediator, so are the threads. Very simple stuff. Anybody can understand it. 10-year-old can understand it. You might have questions, that's something else. But the issue here is, do you understand the proposal, the theory, what we're proposing, what the theory is? And these people start going off on a tangent, and they never answer the question. All I want to know if they understood it. I don't want them to believe it. I don't want them to say, I have knowledge now. None of that. Did you understand it? We explained, they understand, we're done with science. Belief, knowledge, that's religion. That's something else. It has nothing to do with science. What you believe and what you voted for. Okay, so here it is. We look at this word singularity. What is a singularity? And you look up the Wikipedia, peer-reviewed encyclopedia. They say it's not, but it is. Right? A lot of people guarding all these articles. They won't let you change it any way you want. Okay, it says, in mathematics, a singularity is a point at which a given mathematical object is not defined, okay, or a point where the mathematical object, what the hell is that, ceases to be well behaved. Okay, bad boy. Misbehaved. Okay, so that's the definition of singularity. It's a point where the mathematical object is not defined, meaning an equation is not defined. They call it a mathematical object. There are no such things as mathematical objects. And that's the problem. These people start using this weird language, this irrational language, then they introduce it into physics. That's where the problem is. They start talking about mathematical objects and they turn them into physical objects. Just casually it morphs into a physical object. Okay, so here we have it. This is another site. Okay, it's from the National Academy of Sciences. It says the science behind space. Whoa. Okay, let's find out. What is the singularity of the Big Bang? Because the Big Bang allegedly started at a singularity. How did they come up with that idea? Well, they took all the galaxies out there and they say they're all running away from us. Why? Because they're all, redshifted? And redshifted means that, according to the mathematicians, right, that everything is flying away from us if we were going to follow the Doppler effect, right? So it's like, when the siren comes towards your ear, it goes, ee, when it leaves, it goes, ee. So the waves are, spread apart, and that's why they concluded that all the redshift that we see out there is running away from us, so whether it's a galaxy, a star, or a planet, whatever. And the problem with that is that, we do have the local group, like Andromeda, and it's coming towards us, and it's blue shifted. And you say, well, hold it, how come all the galaxies are flying out and all these guys in the local group are coming towards us? They're all blue shifted. What's going on here? And so they answer the question by saying we have gravitational or electromagnetic attraction overcoming the expansion, the dark energy that's pushing everything outwards. That's how they explain it. Okay, so whatever. I'm not going to digress so much, but you say, how did the universe begin? How will it end? The science. Here's the science, okay? The Big Bang Theory says that the universe came into being from a single, unimaginably hot and dense point. So we have unimaginably, that's okay, I can't imagine it, right? Hot and dense singularity. I thought singularity was a mathematical concept, as we just read, right, or heard from Wikipedia. It's a mathematical concept. Suddenly it turns into a hot, dense thing. They call a point or a singularity. So this mathematical concept suddenly becomes a thing. Now they're going to introduce it into physics. They're going to shove it into physics against your will, whether you like it or not. They're going to shove that singularity into physics where it don't belong. It doesn't belong in there at all. It's got to stay in mathematics. It says more than 113 billion years ago. It didn't occur in an already existing space. In other words, there wasn't a point surrounded by space, this dark stuff, this vacuum. No. It initiated the expansion or cooling of space itself. So that little dot contains space. And so what's outside of the little dot? What's giving shape of this singularity? Well, we don't have to worry about that because the singularity has no size, no diameter, no radius, no volume, no shape, no size, no nothing. It's absolutely nothing. And they start with this nothing and say from this nothing something came out. And what was that nothing? Well, it was a point, singularity, a mathematical point, a mathematical singularity. Anyway, it came from a number. From a calculation, from an equation. That's where it came from. Okay, so unless you understand that, you don't understand what these people are saying. Okay, so here we have one person, and she's part of the PBS. I call it BS. I always forget to put the P. Just BS. Bunch of BS. And here she is. She's a caricature of a scientist. She works parallel to this other fellow, Matt O'Dowd, who runs his space-time channel on PBS, on BS, okay? And she says the following. She says, mathematicians use the word singularity to describe a problematic point. First of all, she says describe, okay? The second one, she's talking about a point. What is a point? Well, if we follow good old Euclid, a point is zero-dimensional nothing. It's got no dimensions, meaning it's nothing. 0D, okay? No size, no shape, no diameter, no radius, no nothing. And it says a singularity is a point where a quantity becomes infinite. So they're not talking about physics, they're talking about math. They're saying a quantity is infinite, whatever that means, okay? Because infinite in math just means counting incessantly. And they use the word infinite to refer to counting incessantly, okay? And so that's the part of the problem, their language. It gets weird when that mathematical quantity is supposed to represent something in the physical world. Yeah, absolutely. You cannot convert that mathematical quantity into anything physical. That is the problem. That is the serious problem with the singularity. Because these people take this mathematical quantity, undefined mathematical quantity, this infinite amount, and they say, okay, I'm going to use that now as a baseball bat. No, you can't. You can't use it in physics. But see, that's where they start. They start Big Bang there. And even worse, they use it for black holes. And we got a little problem there because, Big Bang is a bunch of, what do they say, a bunch of concentration of mass that's in there in that zero-dimensional, no-size point. It's all concentrated there, right? And it's going to expand. It's going to explode. It's going to Big Bang it, right? And the black hole is the opposite. It sucks in. And you say, well, why didn't it suck it in, when we had the Big Bang? Why didn't everything just get compressed and stay there? And if anything, compress it even further. No, here they have it exploding. Here they have it imploding. And so we have a problem between the singularity of the black hole and the singularity of Big Bang. They're kind of working at cross purposes here. Okay, so here we have this lady, and she says, the following says, once you reach the North Pole, this is an example she gives, you'll cycle infinitely many time zones during your 24-hour walk, whatever that means. So she doesn't know what she's meaning, but she says, whatever that means, you walk around in circles, but you can't walk around in a circle in a zero-dimensional point, okay? And that's why it's infinite, because there's nothing there. There's no space there. There's no volume. So you're circling nothing. And it's worse than nothing. You're not even circling, because circling would at least require some shape, some space. And here they're saying there's no space, but you're circling. So that's when they say, well, that's why we call it a singularity. And they call the North Pole a singularity, and they call the South Pole a singularity because of that. Okay, so yeah, these people are talking nonsense that they cannot imagine, let alone using the wrong language to present it, because they can't. They cannot transform their math into physics. That's the problem. Okay, so what does good old Matt say? Because he's going to participate here, right? He's going to come in this show from this lady, and he's going to tell us something which is absolutely important, which a lot of people out there are not aware of. And that is that a black hole is absolutely nothing. I talked about that in a video the other day, and people went over the hill there, over the top. What's the issue? The issue is that these people tell you in your face, okay, that a black hole is absolutely nothing. What do I mean by that? I mean that it's zero-dimensional, it has no size, it has no shape, it has no radius, no diameter, no volume. It has no matter, because all matter has been crushed completely out of existence. And since mass is the quantity of matter, it has no mass either by definition. So we have absolutely nothing in front of us. That's the definition of a black hole. Okay? And just in case, so you say, well, that's you, Bill, you're saying that. No, we're going to let Matt tell you that. Okay? So here it is. I'll probably do it a couple times so that you get it right. Here it goes. Listen carefully to good old Matt. Here goes.
What if the massive object itself has zero size? That's the singularity of a black hole, where density and gravity do go to infinity.
Here it goes again.
What if the massive object itself has zero size? That's the singularity of a black hole, where density and gravity do go to infinity.
Okay, so what is a black hole? What is the size of a black hole singularity? Well, it's 0D. There's nothing there. And that's what's forcing stars to orbit around nothing, because it's absolutely nothing. Singularity is absolutely nothing. It's a quantity that has nothing to do with physics, but they're telling you in your face that the singularity has no physicality whatsoever. It's got no shape, no size, no diameter, no nothing, no volume. So the question is, what is a black hole? Okay? Here, all these people are studying black holes today. If you look up papers of black hole in the literature, you'll just be overwhelmed. There's a black hole paper written every second of the day. Lots of people publishing stuff on black holes. And the question is, what are they studying? What are all these people around the planet studying? What are they talking about? There's nothing there. You cannot talk about a black hole because it's absolutely nothing. You cannot say a black hole does this or that. The singularity of a black hole, which is the meat of a black hole and surrounded by this event horizon, which is the region of influence of the singularity, okay? This singularity has no size, no nothing, no diameter, no volume. Nothing is there. And people don't understand that. And then I add to that, just in case to rub it in, that Hawking says this in his book. He says that, Chandrasekhar won the Nobel Prize in 1983. Subramanian Chandrasekhar. He won the Nobel Prize for proving mathematically that a star 3 times or more bigger than our sun collapses to 0 size. So here we have Chandrasekhar. He won the Nobel Prize for saying that. Now we have Matt. Here we are, 2024. He says the same thing. It's got no size, no shape. That's a singularity. That's the meat of a black hole. And then we have, obviously, the problem where, the black hole singularity sucks things in, whereas the Big Bang explodes them outwards. These people are just contradicting themselves. They never resolve their contradictions. They live with paradoxes. Okay, so here it is. We have a singularity, and it moves a star around. Okay, in this case, the sun. It doesn't matter. A star would look something like that. And it's going around this mathematical singularity, which is, I drew something because I wanted you to see something, but really that something is not there because it has no shape, no size, no matter, meaning no mass either, because mass is the quantity of matter, or a measure of quantity of matter. It has no volume, no diameter, no radius. We have absolutely nothing in front of us, and it moves a star far away by what? Remote control, action at a distance, which is another term for witchcraft, black magic. So that's what they have to explain. How does, even assuming singularity were something, how does it do it? How does it affect that star physically? What's coming in contact? What's connecting the star to the singularity? What physically connects it? And unless they can explain these, they have to make an assumption about what object is connecting the two. Then you're talking about black magic. They call it action at a distance. That's witchcraft. That's what it is. Okay, so here are the conclusions for today. Okay, it says the concussions, not the conclusions. I call them the concussions. We're going to have a lot of concussions here. Singularity is a mathematical nonsense, poppycock, but it belongs to math only. Singularity does not belong to physics. It has nothing to do with physics. But Big Bang is known as a singularity. This singularity pushes things outwards. Okay, it's exploding. It's big banging. The black hole, on the other hand, the singularity of the black hole pulls things inwards. We don't know how it does it because they never explain the mechanism. They just say it's mass, but even mass is wrong because mass is the quantity of matter, and they claim that the black hole crushes all matter out of existence. There is no matter, and if there's no matter, there's no mass. See how simple it was? Very straightforward. And so then again, by what mechanisms do the Big Bang and black hole push and pull respectively, light or whatever, inwards or outwards? You got to explain the mechanism. And and then again, how does a 0D nothing, which is what a black hole is, how does it influence matter? Okay, and if you can answer that question, you won't win a Nobel Prize. They'll just say that you're wrong.